Okay, I think we can kick this off. So our first talk this afternoon is Eli Amson, who will be talking about humeral diaphysis structure across mammals. So take it away.
Thank you very much. So hello, my name is Eli, and I'm going to talk about the inner structure of long bones, the humerus in particular. We know that bone structure reflects some functional adaptations. This is typically demonstrated looking at the cross-section at mid-diaphysis, the middle of the shaft, because it is often assumed that the diaphysis structure is uniform and tubular. For instance, the humerus of extant saurians, so manatees and dugong, that you can see on the slide as the second humerus starting from the left, is known to be osteosclerotic, unusually compact, as measured by the classic parameter global compactness, so the ratio of bone over total cross-sectional area. But other adaptations are not as clearly reflected by the global compactness, such as in moles, for whom the midshaft is not particularly compact, as you can see as the last humerus on the right on this slide. So I looked at the humeral structure along the diaphysis in a sample of almost 160 extant mammals, representing each independent acquisition of the most specialized lifestyles. So we recognize the aerial, fully aquatic, and subterranean lifestyles, as well as terrestrial close relatives for comparison. Of course, additional specialized lifestyles acquisitions are known in the fossil record, and for this dataset, I was able to successfully sample fossil bats and talpids, so the true moles. So for the first main result, the general condition for mammals found in virtually all terrestrial species is to increase diaphysis compactness proceeding distally, as seen in the panel A. A similar pattern is found in most subterranean species, shown in panel B, with the notable exception of subterranean talpids, so the true moles, whose humeral structure tends to be more uniform. Aquatic species in panel C show two distinct patterns. Saurians have extremely high values that nevertheless increase proceeding distally. Cetaceans have compactness values falling among those of terrestrial species, actually, but differ in featuring a mid-diaphysal region of higher compactness. Aerial mammals in panel D depart from the general condition in featuring uniform and low compactness values, rather low. The sample extinct species, so subterranean and aerial species, fall close to their extant kin. When computing the slope of these global compactness profiles, it is clear that terrestrial and subterranean species as a whole don't differ, as shown in the panel A, and as I checked with phylogenetically informed ANCOVAs. But aerial and aquatic species do differ in showing more moderate slopes, especially in aerial taxa, and this remains true when the body size effect is encoded for, so putting it as the covariate in the ANCOVA. And as seen on the panel B here, this effect isn't really strong, this size effect, I mean. An ancestral state reconstruction shown in panel C suggests that each of the 5 independent acquisitions of this lifestyle is associated with a decrease in that slope. Concerning subterranean species, the present results showcase that each of the 5 independent acquisitions of this lifestyle is associated with a decrease in that slope. Concerning, regarding the fully aquatic mammals, even though in terms of absolute compactness values, the Saurian modifications appear as the most extreme, they preserve the proximal distal compactness increase found in terrestrial taxa. Cetacean modifications differ in that regard, with compactness profiles showing a central region with slightly raised values. Take-home message here: the diaphysis of long bones is uniformly tubular, but becomes more compact proceeding distally. Deviations from that pattern reflect the most specialized mammalian lifestyles. Thank you for your attention. Thank you to all these people on my slide and to the organizer of the PALAS meeting.
Brilliant, thank you very much. Right on time. Okay, so next up we have Marta Pina, who's going to be talking about new data on the Nacholapithecus elbow. So let's just pull this slide. Okay, here we go. Take it away.
So hello everyone. Today I will talk a little bit about the proximal ulna of Nacholapithecus. Nacholapithecus carrier is a stem hominoid, the superfamily of primates, including living apes and humans. And it was found in a fossil site called Nachola in northern Kenya and dated at the beginning of the Middle Miocene. Well, this species has been described as a large-sized hominoid with strong sexual dimorphism, with males weighing around 23 kilos and females the half of that size. As we can find in most of the Miocene apes, Nacholapithecus shows a mixture of primitive and derived features at the cranium, the teeth, and the postcranium, showing, for example, a configuration of the subnasal region, which is similar to that of extant apes, but a primitive monkey-like body plan. In any case, it has a set of distinctive anatomical traits that differentiates it from other close taxa from the Miocene of Africa. Well, probably it is the postcranium of Nacholapithecus, one of the most interesting things of this taxon. As I said, it has been described as a pronograde primate that might rely on general arboreal quadrupedalism, and it probably had a unique limb proportions with relatively large forelimbs related to the hind limbs, and a series of derived traits that relate to the forelimb-dominated behaviors such as vertical climbing. I will focus today on the elbow of this taxon, since this joint has been very important during hominoid evolution due to its relation to these forelimb-dominated behaviors I have mentioned before. You can see in the middle of the slide some of the most characteristic traits of the Nacholapithecus ulna, which again displays a mixture of primitive features like a long cold cranium and derived traits as the configuration of the radial knot, for instance. So in our study, we took up to 17 measurements on this proximal fragment in the middle, but also on the proximal ulna belonging to the species holotype and a sample of living and extinct anthropoids. We calculated the Mosiman variables to remove the effects of size in our subsequent multivariate statistical analysis and performed some hierarchical clustering based on the UPGMA algorithm with the PC scores. Finally, we calculated the cophonetic correlation coefficient to check the fit goodness of the clustering. In our results, the PCA clearly separates apes and monkeys, and within apes, great apes and hylobatids. Nacholapithecus, black arrows and holotype highlighted with an 8, falls within the Cercopithecus morphospace, particularly within the space occupied by large papionins. The closest fossil taxon to Nacholapithecus is Equatorius, the other genus within the tribe Equatorini. And it's the same for the dendrogram, where Nacholapithecus is clustered next to baboons and within a group including papionins and the fossil taxon Equatorius. Well, all these taxa are characterized here by a relatively long old cranium and a mediolaterally narrow and shallow anteroposterior epiphysis. All these traits have been associated with quadrupedal behaviors and even with terrestrial habits. But however, Nacholapithecus differs from papionins by displaying a different configuration of the radial knot and a wider width of the coronoid process. Interestingly, all the most terrestrial medium-sized quadrupeds in our sample, including baboons, mandrills, and chimpanzees, are placed close in the morphospace and separate from other taxa, as you can see within the black circle I've drawn. They are all clustered in the same group, together with other extinct hominids that display a more derived morphology of the proximal ulna, which are Gryphopithecus at the top and Hispanopithecus. So summarizing, Nacholapithecus shows close ulnar morphological affinities with large papionins and the extinct taxon Equatorius, which are characterized by these ulnar traits that you can read here in the second point. And these results are compatible with previous works that suggested Nacholapithecus might be a general arboreal quadruped, already incorporating within its locomotor repertoire some antipronograde forelimb-dominated behaviors such as vertical climbing. And finally, our results might suggest the presence of some terrestrial or semi-terrestrial habits in Nacholapithecus, a type of locomotion only described actually for Equatorius before. But nonetheless, some of the traits related to terrestriality are still controversial, and the results on the ulna need to be integrated in a wider context, considering all the current evidence that we have so far for this taxon. Thank you very much for your attention.
Brilliant. Thank you very much. Right on time again. So next up, we have Sean McCormack, who's going to be talking about Could Lucy Run?
Hi, I'm Sean McCormack, and as you said, I'm going to be talking about the question, could Lucy run? Lucy is an Australopithecus afarensis fossil. I just want to quickly thank Palas for the undergraduate summership funding, and also my supervisor, Karl Bates, for the opportunity. Okay, so the motivation behind this research is the thought that running may have been a key selective pressure in the evolution of whole body functions and structures of the human anatomy. A high profile example of this is the endurance running hypothesis, and this suggests that numerous hallmarks of human anatomy can be explained as adaptations to long distance running, which was necessary for obtaining food by scavenging and then later persistence hunting. The hypothesis came about from the comparisons between our body and that of non-human apes, including the Australopithecus afarensis. Some of the notable differences between us and non-human apes were actually make us more adapt to being good runners. This includes the nuchal ligament, which helps to stabilize the head during running, and it's not found in the Australopithecus. Also, body proportions differ. We have an increased lower limb length and decreased upper limb length, which improves performance and decreases energy costs when running. Humans also have increased joint surfaces in the lower limbs, or the lower body, sorry, and this can impact, because the impact force increases 3 to 4 times when running. This helps to reduce that force. There are also multiple modifications in the foot. These include the plantar arch, which has an elastic spring function, and this helps to create energy when running. Humans also have an extremely smaller toe length compared to other animals, and this is advantageous in running. The Australopithecus toe length were found to be intermediate between humans and non-human apes, and this can actually reflect a trend of toe length decrease as the primate species moved away from tree dwelling. However, in the last 5 to 10 years, there's been a lot of work done on the walking mechanics in the Australopithecus, and this work has changed the view of their ecology and locomotor ability. The Australopithecus were originally thought to be more arboreal than terrestrial, but the interpretation of fossils, fossil footprints and biomechanical models has suggested that they are probably quite more upright, competent bipedal walkers, and so their gait actually might be more similar to ours. So because of these new findings and the overall importance of running on the evolution of the human anatomy, it's quite surprising that there's been no quantitative assessment of the running ability of the Australopithecus, and so this is why we wanted to do this research. So the overall aim of this project was to produce a biomechanical model that will predict the running ability of Lucy, and I completed the first stage of this in my summership. So what I did was I gathered muscle mass data for the majority of the lower limb musculature from MRI scans from published papers. I then made muscle origin cutouts using mesh lab of human and non-human apes, including Lucy. For each muscle, we then ran a lot of different regression models. We found the least squared regression model to be the one that fit the best. We hope to then use these models and equations to predict the size of Lucy's unknown muscle mass by plugging in her known origin attachment sites. I looked at nearly all the muscles in the lower limb, but the gluteus maximus and soleus were found to be statistically insignificant. So the results are seen here on this slide. Looking at the graphs, our results suggest that Lucy tends to be an intermediate between human and non-human apes in the muscle mass percentage, and it's seen most clearly in C with the some muscle mass. Just some points of interest. In A, you can see the hip abductors, which includes gluteus medius and minimus. These are key muscles in humans for the medial-lateral stability during walking and running. And our assumed muscle mass of the gluteus minimus and medius in Lucy was much smaller than it was in humans, and it was actually closer to the non-human apes. And in chimps, these muscles are actually known to be extensors rather than abductors, which means they're less adapt to running. Also of note in B is the gastrocnemius. In Lucy, we assumed again that it's a lot smaller than the human, which could be of importance as the gastrocnemius is a very important ankle extensor, which is known in many species, such as birds as well, to be a key adaptation in fast running. So as Lucy doesn't have this adaptation, it can be suggested that she also could not run. And this is also supported by the fact that Soleus was statistically insignificant. So just to conclude, Lucy is therefore likely to be an intermediate in the primary evolutionary selection of running. Thank you for listening.
Okay, brilliant. Thank you very much. Matthew Cohen, who's going to be talking about new insights in morphology and histology of Triassic Hybodontiform shark fin spines. So yeah, take it away, Matthew.
Hello, everyone. Welcome to my talk. Today I'm going to be talking about some Triassic Hybodontiform shark spines. This talk contains some unpublished material, so I must ask that you not share anything on social media. So for anyone still hanging around from the mammals talks, perhaps, Hybodontiform or hybodont sharks are a major clade of elasmobranchs from the Devonian through to the early Cenozoic, and they're distinguished by their conical teeth and, relevantly for today, their pair of dentinous dorsal fin spines. So this study began with 3 dorsal fin spines from the Triassic of southwest Poland, from the Kuiper bed strata of the Poręba and Lisowice localities. Dorsal fin spines are not unique to hybodonts, but they are present in several fish groups, including other elasmobranchs, both extant and extinct. Our spines here are incomplete. They are all missing the tip section, and only one of the spines preserves the unornamented basal section, but they are all well preserved with the material that is present, and they're all identifiable as hybodont spines based on their posterior, which is convex, their costate ornamentation, and the rows of denticles present. Beyond the fact that they are hybodont spines and they feature the classical hybodontiform features, we can't identify them to any extent, say, to the species or generic level, as this is impossible without the teeth. But if this is all that we can really say for the histology, what about for, for the morphology, what about for the histology? Well, to examine that, I took a transverse fin section from the tip of one of the spines from the Poręba beds, which you can see here. I took my fin section from the tip of the spine specifically because this is the easiest part of, this is the earliest part of the spine to form and is therefore the most developed. And in this part of the spine, we can see the full range of tissues present in hybodont spines, both the inner lamellar tissues, which enclose the central pulp cavity, and the structured trabecular dentine that forms outside of this. Because we're looking at the the tip portion of the spine here, we see much thicker lamellar dentine than we would at the base of the spine, as this forms later in the growth of the spine. What's interesting about the lamellar dentine is that it exhibits colored banding, including darker bands, which appear to indicate more distinct breaks in the growth of the dentine layers, and thinner bands, which we can see more closely in image 1 on this slide. The dashed lines are showing the darker bands present in the lamellar dentine, and the arrows indicate the thinner bands. Now, the thinner bands appear to be growing fairly consistently, so in terms of thickness, which suggests to me that they're growing in a regular fashion. In other shark fin spines, this sort of structure would perhaps be indicative of tidal effects, or more interestingly, perhaps, it could be used to form a basis for calculating the age of the shark. Now, we can't do this because our spines are incomplete, and methods that have been used for aging sharks in other fin spines are reliant on tissues that are not present in hybodont fin spines, such as enamel. But the inner lamellar dentine bands, which is what we do have, these have been used to provide ages for chimeras. So it certainly seems plausible that these structures could form the basis of a method for aging hybodonts, which would provide a valuable new avenue for exploring the life cycles of these animals. Thank you for listening.
Okay, brilliant. So if I could just ask all of the speakers to turn their microphones back on, and then we'll start the panel discussion. So we already have a couple of questions that have appeared in the chat, but if anybody else does have any questions for any of the speakers, please type them in, and remember to flag them in chat with the chat mode versus question mode button just above the box that you type your response in. So I think we have 2 questions, both I think directed at Marta. So we have a question from Zoe Kiningopoulos, who says, "Great talk. I'm so glad to see that you were able to work on part of the ulna. Did you use the linear measurements for the PCA, or did you correlate the data, since animals used to have different weights? And if so, what type of correlation? So ratios of the measurements, for example."
Okay, thank you for the question. Yeah, we used the linear measurements, but as I commented, we calculated the Mosiman variables, and this implies to calculate the geometric mean with all the measurements, which is a way to, like, a surrogate for the body mass. So we are removing all the size effects on the results, and all you have seen in the plot is morphology related.
Okay, brilliant. So second question also from Marta. So Fabio Alfieri, he says, "Nice talk, Marta. Are there any other postcranial specimens available for Nacholapithecus?"
Yeah, thank you for the question too. Yeah, I will say that virtually we have all the elements of the skeleton. There are a lot of remains of Nacholapithecus derived from really intensive fieldwork campaigns since the late 80s, I would say, from Japanese Kenyan teams. And yeah, but the only problem is that most of the elements are crushed or deformed. So yeah.
Okay, great. So does anybody else have any questions for any of our speakers? Just type away in the chat.
Actually, if there's time, I have a question.
Okay, yeah, sure. Yeah, if any of the speakers have questions for the other speakers, that'd be fantastic. Yeah.
So for Sian, sorry if I mispronounce your name, about the knuckle crest, knuckle ligament adaptation you mentioned. Is there a osteological correlate to that on the, I guess, on the spinous processes of the vertebrae? And if so, how is it how does it compare in Lucy compared to other Homo?
Okay. Yeah, so in the skeletal fossils that we have, or the skeleton we have, you can see it creates a ridge on the occipital bone if the ligament was present, and that was found in the Homo, but it wasn't found in the Neanderthal. So Lucy, yeah.
I see. Thank you.
No problem.
Okay, brilliant. Anybody else? Okay, we still have a couple of minutes, so if anybody else has a question they want to ask, then please type away in the chat. Okay, great. Well, I think, so we don't seem to have any more questions coming in, so I think we can, oh, hang on. No, we have a question. So we have a question from Manabu Sakamoto. This was for Eli. So he says, "I'm really intrigued by your findings. I can't quite remember now, but did you estimate transition rates between the environments? That is, are one transition more likely than another?"
Yeah. So I had no assumptions, like a priori assumptions regarding the one transition being more likely than another. So I used the equal rates. Yeah.
Okay. Any more?
And before we move on to the non-Rankian or taxa, Jakob has an urgent follow-up: stem metazoa or stem eumetazoa?
Okay, brilliant. So I think we can wrap up and leave it there. So I'd like to thank all of our speakers again for their fantastic talks and for keeping to time as well, even in light of a few technical difficulties. So yeah, it's been really great. So yeah, thank you again, and I hope I'll see you again for the rest of our sessions later. And as Jack says, we've got a whole program of exciting things coming up this evening as well. So yeah, thanks again.